So like I mentioned previously, my name is Lou. Today I'll be presenting to you some MLOps going from level 0 to level 1 to help you make your pipelines more efficient and more effective when training your machine learning models. Just to get started here, I'll give you a quick outline for today. We'll introduce SuperAnnotate, tell you what we are doing in the machine learning space. And then we'll go into an introductory ML sports analytics project that I've been working on. I'll outline some machine learning operations that I've implemented for the project. And then we'll also look at how to integrate SuperAnnotate into that type of workflow. And then we'll go into consider further things that might need to be implemented once you really have the need to scale up. And then at the end, we'll obviously do some Q&A for any folks that have any questions about the process. All right, so SuperAnnotate was founded by two brothers, Tigran and Vahan. They were working on their PhD in machine learning and computer vision. Vahan came up with a super pixel algorithm, which allows people to annotate more accurately and quicker. And so the platform kind of is based around that idea, but it also allows you to collaborate with other people, create data sets, label them, curate those data sets. And so we were founded in 2018. Up to date, we've raised about $20 million. And we're a global team located throughout the US, as well as Armenia, Sweden, and Bangladesh too. We are ranked #1 on G2, which is great to know that people enjoy using our product and services. A little bit about what we offer here at SuperAnnotate. We have a data ops platform, which includes, the software itself to do the labeling. We have an SDK that can integrate into your machine learning pipelines. And we also have a way to review and give feedback on those annotations. Our data ops services would be if you would like to outsource your current annotation job. If you want us to take care of all the labeling, we provide that as well. We can talk about what the project entails, what kind of labeling instructions you would need. And based on that type of communication, we would be able to tell you exactly how we would be able to move forward. We also offer MLOps integration. So you have the ability to talk to someone that's an expert with this type of technology. And you'll be able to also leverage their expertise to help you build out components for your pipeline. All right, so we'll introduce now the sports analytics project that I've been working on. It's based on the ability to measure how high someone has jumped. So usually the way that this goes, we use a Vertex. It's a machine like the one on the right. You stand up and you reach as high as you can with your feet on the ground. You mark that height, and then you take a jump and you touch the highest point. And then you can measure the difference between your standing and vertical jump height. While this does allow you to accurately measure your vertical jump, it can be kind of costly. These machines go for about $750. And they also only allow you to measure between 6 to 12 feet. So those are some of the limitations here. Another commonly used method for measuring vertical jump is a force plate. So you'll have the athletes stand on top of this force plate here. They'll go up into the air, and then when they come back down, you can measure how much time was spent in the air by measuring the force contact time points. This allows you to accurately measure vertical jump, but like the previous solution, it is also very high in cost, anywhere between $1,000 to $5,000. So I've been trying to work on a solution that can kind of provide the same output, the jump height, but in a much more low cost manner. So I'm planning on using computer vision, using a camera from your smartphone to kind of just take a video of someone jumping, and then using artificial intelligence to kind of classify which frames the person was on the ground versus in the air. And then if we want to go into some more detail, we can talk about how you can convert the time spent in the air to the height that the person has jumped. But that's the general idea, inputting a video or a bunch of frames, getting a machine learning algorithm to classify those frames, and then output some type of jump height. The output's going to be a numerical value in inches and centimeters. And the input, as you can see, is a whole bunch of frames, and each frame is going to have a lot of data in it. It's going to have, depending on the resolution of your video, upwards of 1 million pixels. So that's a lot of data. Sometimes it might contain a lot of noise that is not needed for your actual calculation. And so we'll go also through how I kind of dealt with that issue. There were two methods that I implemented. The first method was a baseline, just to kind of get an idea of what neural networks would be able to do. So I had one convolutional neural net that was just predicting air or ground for each image or frame of the video. And based on the amount of frames that you were in the air, you'd be able to calculate the height. It wasn't too accurate due to the fact that it's kind of difficult to really tell when a person is on the ground or in the air, just based off the entire frame. So I decided to implement another method, which includes 3 models as part of the pipeline. So 2 models would be used for feature extraction and 1 model for classification. This method was a lot better at reducing the noise and actually getting more accurate results. And I used the SuperAnnotate to kind of help me develop these models as well as measure the performance. So for the first method with the CNN, very basic, all the frames would go into the convolutional neural net. The only labeling that is actually required here is just having the training set divided into in the air or on the ground. So there's really no like annotating here on a pixel by pixel level. You can tag the entire image as just on the air or in the ground and separate that into a different folder. And that's how you could train this neural network. The neural network outputs its values, which go into some type of physics calculations. And then those physics calculations finally output you the jump height. The second method that uses 3 models, this is more or less the flow. So initially you have your video, you go into an object detection task provided by Detectron 2. So this will select a portion of the image and draw a bounding box around the person. You can then extract that portion of the image with just the person, eliminating the rest of the pixel data, which is kind of noisy and doesn't really relate to whether a person is on the air or on the ground. Then I would use a key point detection algorithm, also based off of Detectron 2. And the key point detection model would pinpoint exactly where the joints of the person and the image are. Once that information gets extracted, it could be fed into a KNN classifier. And this is where we now classify the joints list as whether it's in the air or on the ground. And that once again gets input into our physics calculation, which gives us our jump height. So this second method is a lot better in extracting the proper information that we need. And so this kind of should give you an idea of how a problem in machine learning can be kind of broken down into a subset of problems. And that's kind of where SuperAnnotate can help us a lot in creating these different types of models that are good at specific annotation tasks. And then you can extract the relevant information from there. So to kind of reiterate, I wanted to create a computer vision system that replaced the physical measurement devices we saw in the beginning. What SuperAnnotate will help us do in this case is label the data that we have accurately and make it available for training. We'll also be able to create different data sets. So, I need one data set for the bounding box problem. I need a slightly different data set for the key point detection problem. And so SuperAnnotate can help us create those different data sets. And then finally, we have the ability to have a human in the loop, which provides the ability to quality check, make sure the annotations are correct and accurate. So that gives you some feedback on your data quality through a human. And once again, the 3 models that I used for the second method are a bounding box object detection, which, like you see here, gets just the person in the frame, removes the rest of the pixel data. And then a key point detection algorithm will delineate where my joints are located. And these joints should have some correlation to whether a person is on the air or on the ground. So that will be decided by this KNN classifier. Okay. So now that we know the project and kind of what it's attempting to do, we can talk about the MLOps portion of this webinar. So this is kind of an introduction to all the different steps that might be included in some machine learning projects. You have the data collection portion, verifying that the data is usable. We have feature engineering, and then your machine learning code, which is your training, as well as the model that gets saved. That is a small portion of the machine learning ops pipeline. So we'll dive into a few of these today. We also have obviously the ability to serve the model for our clients to use. We won't be getting into that much today, but just know that that's also a part of the MLOps workflow. All right, diving into MLOps level 0. This is pretty much a level where everything is manual in your pipeline. So we have some offline data here. It can get extracted and analyzed before being prepared. And this is where we would actually be able to provide a lot of help with SuperAnnotate. We can prepare your data by annotating, labeling, doing quality checks, making sure that everything is accurate. And so once the data has been prepared correctly, we would have to manually again move or transfer the extracted features to our model training step. Here is where the model would begin its training, and depending on specific evaluation and validation metrics, we would be able to, once the model reaches a specific threshold of accuracy, we can then save that model and output it to some type of model registry, where we keep track of the models that we're training with specific versions of our data. So that's the ML portion of the MLOps pipeline. The ops portion over here is putting the model into operation or being able to have it in production for clients to use. You'll be able to go to your model registry, which has saved your models. You'll be able to put it onto some type of server, and then that server can provide the prediction service for your application. There's also a difference between the experimentation steps, which are kind of what you see up here, and then the production, which currently is not really much. It's just kind of having your prediction service readily available for your customers. So yeah, MLOps level 0, it's an entirely manual process. It's usually done to evaluate the feasibility of your proof of concept. So this is what I began with. I trained a model manually. I did all the manual steps. And so all the things that trigger each step of the pipeline were done through the keyboard and at a specific point in time. So everything from pre-processing my data to uploading it to SuperAnnotate. Annotating obviously is going to be most of the time manual, though we'll talk about how we can kind of semi-automate that. And then downloading our data and providing any post-processing that might be needed. All of this is all manual. This is a list of all the steps that could be included in a particular ML workflow. For my project, I think these are the steps that I was actually doing. So for pre-processing, I had to convert the file type from the camera that I was collecting. It wasn't supported. So I had to convert that to a different codec, transferring the data to SuperAnnotate, and then providing maybe quality checks. So let's say my particular project requires only one bounding box per image. I can write quality check scripts to make sure that there's only one bounding box per image. But quality checks can be varied, and you can come up with many different types of checks. Uploading model pre-annotations is a big part. So being able to leverage a model that kind of already does what you're trying to do, maybe not 100% accurately, but good enough, where you can use those predictions, view them on the platform, and then adjust them or edit them if they are incorrect. And then being able to download that data that you've either annotated from scratch or corrected. And then any post-processing that needs to be done, converting to a different type of format, XML, CSV, or a different type of JSON format. All these steps are kind of part of my level 0 project here. Let's move on to level 1. So if we want to go from our proof of concept, it works, it looks like it's feasible, we can move into level 1, where we'll be able to automate pretty much the ML portion of our MLOps pipeline. So all of this part here, beginning from, we could have a feature store where we have already data that's been processed and kind of extracted the important parts of it. We can import it into our data validation, data preparation pipeline. And all of these right here can be triggered now through some means. There's various ways that we can trigger these different steps of the pipeline. I'll go over a few in a little bit, but essentially now this entire portion of the ML workflow has been automated. And once it's been automated, the model's been validated to some criteria. We can take the source code responsible for that, and we can kind of version it. So you have a Git repository, you can have GitHub, Bitbucket, GitLab, and so on. And so that's kind of where you'll have all the code responsible for the all these steps here. So this is on the experimentation development side. And now we see that on the staging and production side, we also have a similar pipeline. So it's kind of mirrored so that whatever is happening in our experimentation can also be part of the automated pipeline on the production end. So on the production end, we have pretty much the same workflow here. We might have a machine learning metadata store, which kind of gets data from the model itself that's being trained. We can incorporate that into the pipeline and then save our model as well after it's met some type of model validation criteria. So like this portion right here is automated. This portion right here is automated. The only thing that isn't automated at level 1 would be this continuous delivery portion, which is kind of related to putting out the models into production in an automated manner. So we'll talk a little bit more about this in a little bit, but just to outline some possible steps in level 1, you'll have the same as you had in level 0, but now you'll have the ability to have continuous training for your model. So your model can be trained without manual intervention. We can get the monitoring of the performance of our model. We can deploy this. This would be obviously a manual step in this case, in this level 1. And then we have the ability to experiment. So we would be able to have different models maybe, or we can have the same model with different hyperparameters, testing out different things to see what works. And all of this is more easily done when we've reached level 1. Just to kind of go over the concept, the transition is automated between each step. Continuous training of our model in production is now available to us. We'll go over some options for triggering. For options for triggering each step of the pipeline. And then we can see that, like I mentioned previously, we have the experimental and operational symmetry. So whatever we're doing in development can be mirrored into our production environment. This allows us to easily test out something in our development, and if it works, it looks fine, we can push it to production. And then the ability to modularize our code. So there's going to be certain components of our machine learning pipeline that we can reuse for certain things. For example, maybe ingesting our data, doing some type of pre-processing on the data, and maybe transferring data from data source to data source. So those types of components should be able to be easily shared across your machine learning pipelines to be able to scale quicker. All right, so how can we integrate SuperAnnotate to pretty much provide this type of machine learning operations? First of all, we have the ability to obviously upload data to our platform manually, which would be kind of if you're in level 0, so you can choose your files from a local directory, or you can maybe even connect your data source from your S3 bucket to our platform. And then through the user interface, you'd be able to upload your data. What we can also do is we can use use our SDK to connect data from either AWS or our local machine. in an automated manner. So that's where our SDK kind of comes into play here for helping us automate most of the things. And we might actually have an example here. So this is a pipeline for a project related to what we're talking about. So we'll begin this pipeline here. And we'll be uploading kind of this this video file here. That video file is actually just a video of me jumping. So that's the video that we'll be uploading to SuperAnnotate. It was recorded at 240 frames per second. It's only about 3 seconds, but because it was recorded at such a high frame rate, there's going to be like 900 or so images, 904 here to be exact. Yeah, so we will take a look at that in a little bit as the data gets uploaded to the platform in a sec. We can then, annotate the data, make sure that we have our labels correct, and then we can download the data. Once again, if you're at level 0, you can come to our user interface. You can select the different formats that we offer to download, such as Cocoa, if you're interested in that, and then prepare that download and get that data for those annotations to your end. Now, once again, using our Python SDK, you would be able to automate this step based on certain triggers that we might place. We have the ability to kind of have webhooks on our platform. I'll get into that in a little bit, but essentially you'd be able to finish annotating an image, set it as completed on our platform, and the data would automatically be transferred to your end in the format that you would desire. Okay, so versioning your data is going to be very important when your data sets start getting larger and maybe you have more of a complicated setup. So essentially what that allows us to do is you can select the entire data set if you would like, or you can select a subset of your data, and you can create a name for that particular subset. And what this allows you to do is, for example, I have this subset here set as ground. So all of these images should have a person on the ground. And this right here can now be pulled via our SDK and used as training data for a classifier that wants to classify people on the ground. Okay. We have the ability to upload annotations from a model, so that can kind of make the workflow more efficient. You can use our Python SDK, upload your predictions, view the annotations, and then you can correct it if you need to with our built-in editors. Once you've made those corrections, you can once again subset the data, version it, and then re-download that data to retrain your models with the corrected annotations. So this is very, very powerful. It actually allowed me to do something on our platform. So let me check real quick. This should be our new project. We can see here that we have that new video file with 904 items. And so what I initially did is I worked on these manually. So I manually annotated these, about 100 images or so. And then I was able to leverage one of the neural networks on our platform, use that labeled data to train that model, and then use the model to annotate the rest of the images. So out of the, let's say 900 images that needed to be annotated, I annotated 100, and then the remaining 800 were annotated by my model. And so then I can come in here and explore and check out to see how the model is actually annotating and performing. And this is where we would be able to version out some of our data sets. So let me get rid of this. Part of the ability to explore your data is also the ability to quality check and use the human in the loop. This allows you to have multiple, if you would like people doing quality checks. So you can have your first round, have people look through the data. If everything seems good, you can have a second round. If everything seems good, then you'd be able to now have confidence that your annotations are of high quality. And what also we can do with our explore feature is filter out your data based on a bunch of metadata information available on the platform. So if you want to check out a specific annotator that's working on images, you can just filter out those images. If you want to focus on a time window of when the images were annotated, maybe you want to look at just the last 3 days of annotations or the last week. Explore through different classes that you may have. There might be a class that you see your model not performing that well in, so you want to really check those. We can even check for the number of instances that are in your data. So you have the ability to really filter out and explore your data in a variety of ways on our platform. So yeah, if you have a task such as object detection or instance segmentation, as well as semantic segmentation, you would be able to leverage our models on our platform for these tasks. But once again, you would have to have a manual starting point where you annotate a subset of those images yourself manually until the model starts picking up on the patterns. And then once the model has a decent performance, you can start using the model to start automating this part of the pipeline. This is an example of different models that I've trained on our platform. So I have a person detector where I annotated 1,880 images. And then I have another version of, let's say, a feet detector, which is just detecting the feet on the image. This one has 105, and this one down here is only 59. So here you can see the different versions that I've annotated. We can also compare their performance, for example, their bounding box, mean average precision. And then you can use the model that has best performed on your data set as your model for annotation. And then as you continue to train more models with more data and the model gets better, you can start using that model. And if for whatever reason you use more data or you have a new data set that you train a model with and the performance drops, you can always revert back to the previous model that was performing better. Okay, so that kind of brings us to the ability to continuously train. So we can retrain our model once new data is available in this method. There are a bunch of trigger mechanisms that can help us automate this process. Two of the main ways are cron jobs as well as webhooks. So a cron job is going to be a script that kind of runs on a server at a specified frequency or at a specified hour or date. You can select it to run maybe every hour. You can select it to run once a week. So that's kind of one way to have consistent maybe data uploads or data downloads. And then the other way is through our webhooks. So we have webhooks on our platform that allow you to trigger events. So let's say you have an entire folder of images that need to be annotated. Once those images are annotated, we'll have a webhook that kind of triggers any type of script that you would like to happen after those images are annotated. So we can have a conversion script to convert all the annotation data to your format. Maybe we'd have an extraction portion where you want to extract a specific area of the image based on an annotation and re-upload that to a new project on our platform. That's also possible through our webhooks. And so, yeah, these are available in our in-house orchestration tool that we have currently. But we are developing this out to have the ability for clients to use this on their end as well. This is a list of the events that we can trigger these webhooks on. So for example, if you've completed an item or if you've set it to quality check as well as returned, these can be the triggers that activate the script that you need to run. So if you send an item to quality check, we can have a quality check script that runs all the checks necessary for your particular project. And if there's any issues, we can automatically then with the SDK return those. Or if there are no issues, you can really pretty much do anything you would like after that. There's also, for example, the project status completed. So if you've completed a project and you've set the status to completed, we can run a script through the entire data set as well. Okay, that brings me to the CI/CD portion. So This is continuous integration and continuous delivery. It allows you to kind of make changes to your code base, apply those changes, and then continually deploy those out into production, and then to monitor any issues or anything like that. If you do encounter any issues during this process, you can revert back to the previous code base that you had. So if things break, you can be assured that you'll be able to revert back to a working version of your application. This is also where we run into the concept of Git hooks. So Git hooks are webhooks, are a specific type of webhook that allows you to trigger a script or anything like that based on a Git command. So when you Git push or Git merge, Git commit, you can have specific scripts attached to either check your script for errors or test your scripts. And that's kind of how we are able to continuously integrate into our project. If there's any issues or errors during this integration step, you'll be notified and the code won't actually merge. You'll be able to go back and check your work before you actually push these changes to your production. And then this is kind of where it also starts expanding out on the amount of tools that we can use. So for this type of orchestration work, there's many tools out there that you'll have for different parts of the pipeline here. So for building and testing, you might have CI circle. You might have different options for deploying and for operating here. One of the examples would be Kubernetes and Docker. So with Docker, you can containerize each step of your pipeline. So for the training portion, the validation portion, maybe the data preparation portion, all of those can be containerized into a standalone unit. And then with Kubernetes, you'd be able to kind of dictate when those specific portions of your pipeline get run. And you can, exchange data between pipeline components. So if you have any data that gets created during your pipeline, you can forward that or pass that on to another part of your containerized application. Great. So this brings us to things to consider if you're going to go to level 2. We won't actually get into much into this. I just want to mention that there is a level 2 here. The level 2 would contain obviously all of the things in level 1 where your machine learning pipeline is pretty much fully automated. But it also then allows you to kind of continuously deliver those models into your production servers for your prediction service, and then to monitor that, provide feedback into your continuous training loop, train another model, version that model once again, and then if that model meets the criteria for performance, you can once again deliver it into production and have a continuous cycle of training, delivering into production based on any new data that comes in. All right, I think that is going to be the end of this one. I'll open it up now for some Q&A. All right, so I guess I'll start over here with how did you do the physics calculation to get the jump height? The video can't retrieve height information without prior information. Good question. So prepared a slide for that, just in case. This is the calculation that I'm using. So here you can see that the real thing that we need is time. We're going to ignore the initial velocity since we're going to measure from the top of the jump, which would be no velocity, and then to the bottom of the jump, which would be the highest amount of velocity. But essentially, if you get the time spent in the air by a person, which would be calculated by having the inverse of the frame rate multiplied by the number of frames spent in the air, you can plug those numbers into this right here, and it would give you the change in height based on the amount of time spent in the air. So that's the general gist of how to use the physics for this particular problem. Next question says, what model registry do you support and how do you allow extension to new model registries coming? So currently the models that we have on our platform are our in-house models. They are based off of the Tectron 2. So they would be able to be kind of versioned in the way that I showed up here in this way here, where you'll have obviously the name of your model, you'll have some metrics associated with it, and then you'll have the data set that you've used to train it. So that's currently how we're doing this. But yeah, in the future, we'll probably provide a more sophisticated interface for versioning our models as well. I see another one here. It says, using a neural network to annotate your data set is powerful, but I could see how it might enlarge the bias the network already has if not properly checked by a human anyways. A human correcting these annotations might get lazy though. What are your thoughts on that? Yeah, I completely agree. I think just relying on the model itself would be a little dangerous, but the ability to kind of explore our data set. So hide this here. The ability to explore your data based on different characteristics. So let's go here. Let's say, let's jump into this one. And so reviewing the data by a human can get tedious, but we have the ability to kind of maybe filter out specific instances where we might be more concerned. For example, here I have a query that I've written for our data set. So this will, let's say, pop out a few items from the data set. And then we could come in here, maybe just focus on the left foot index and then show the classes. So we can see the class tagged on here as well as the key point on it. We might also be able to maybe zoom in a little bit. So yeah, the query system on our platform allows you to focus on a subset of instances which might be troublesome. So that kind of prevents you from having to check the entirety of the data set by yourself. And you can have multiple people also working on different checks. So that's one way that we would kind of deal with that problem, which can be kind of, I guess, important. So it asks, do you support any model to be hosted or only the model that you presented? So we don't host any models on our platform, but we can leverage any model that you have. So we would use your model to provide predictions offline on your end. We would take those predictions, place them into a JSON file of a specific format, and then we would upload those JSON files through our SDK to our platform. So that part is also very automated. And then you'd be able to see all the annotations of that model on our platform as well. Actually, all of these here are, I used media pipes, Google media pipe key point detection. And these instances here are actually all from that model. So yeah, I leverage the model in this case to annotate all these key points because it's very tedious and time consuming. So yeah, you can definitely incorporate pretty much any model into our platform. We have a continuous training question. The assumption is data is going to keep changing, and when the accuracy becomes lower than a certain number, what if the data is sinusoidal in style? Then continuous training model is just going to keep training and data and doesn't find the pattern of the data set. That's a good question. I'm not actually sure on this. Oscar, is there anything that you might have for this?
Yeah, it's a very interesting question. Hello, everyone. My name is Oscar, also part of the team together with Lou here. So the interesting thing is that it all depends right on, if you have data that is changing with some pattern, you might want to have something that fits for the moment, right? If we have, I think sinusoidal would be great to see it in terms of a just function that you try to fit. But if we see this as something, say in the computer vision domain, as unstructured data that we might see with the seasonal changes, you might want to have something that tries to generalize over the seasons, but might not always work, right? So if you do continuous training and retraining, it might fit the best for the moment when the model is actually used. This is also so the model actually adapts, because there is a lot of data drift in different sources. So having something that leverages continuous training can actually help you, because with sinusoidal data, right, you can find a function that kind of takes into account the time span of it and like the temporal changes. But in some other applications, it's like hard to find a function that takes that into account. You usually don't see, say, the timestamp as a function that the deep learning models here could take into account. So with unstructured data, you want to have something that fits for the moment, and then continuous training helps you with that. Like you capture it right away. It could be for other things as well. Like if you have some kind of natural data drift in terms of, modeling, say, I don't know, customer churn or something else, that might be something you want to update very frequently, just because it changes over time. So your data is drifting and you want to catch that. So it's rather not really a lack of finding the pattern. It's more like, it will find the current pattern, which is what you're looking for. I hope that sort of answers that question.
Yeah, thank you, Oscar. So we have two more questions related to the project itself, asking about how I calculated the height of a pixel as the distance to the person or camera will vary. I imagine that's so it's independent of pixel calculations. It's strictly based on just classifying whether a person is on the ground or in the air. We can I guess if you'd like to talk more about this, we can definitely meet up. Follow me on LinkedIn. I guess we can chat a little bit more about that if you're very interested. Don't want to bore everyone else here with the details. And we got next one that says, is your platform capable of triggering model conversion from, let's say, PyTorch to CoreML TF-Lite automatically and run it on test images? Also, can your platform do this across Linux servers, macOS, IoT devices? So for the first part, we don't currently have any model conversion functionality. That I guess, yeah, it depends on what you're trying to do there. But I imagine if you have your predictions of your model, any model can be incorporated into the platform to visualize the data that you're annotating. Yes, it would be -G. You're correct for the acceleration. All right, awesome. I think those are all the questions I have on my end. Once again, I want to thank everyone for joining. I appreciate the time and the attention. And yeah, we'll be continuing more webinars here at SuperAnnotate to kind of help you look at the types of problems that you might deal with and maybe come up with some type of solution for those. So thank you, everyone. I appreciate it.